Hi, and welcome to module number 48. Recall that the series of modules that we're going through, we started with sparse recovery, and then I was saying in number 47 that we'd like to go toward optimal sparse recovery, but there are a lot of different types of optimality, and you would want to understand the design space and think about where you are in the design space with your application, what's important to you, and that'll allow you to make choices that will likely lead to a better algorithm that'll perform better. And if you just use some random off-the-shelf algorithm without thinking carefully about your design space, you might get what you didn't really pay for. And now in the current module, I'm going to start talking about information theoretic performance limits. And we're going to start describing some of the selections that we've made within this design space. And in the next modules, this will be building toward a reasonable complexity algorithm that gets good performance for a somewhat wide range of problems, as you'll see. So the fundamental goal here is really to minimize measurements. Compressed sensing is aiming to reduce resource consumption due to measurements. Resource consumption could be power in electronics, or it could be the rate of an analog to digital converter. For example, it may be extremely costly to push the next 20% of speed, or it could be something completely different. But again, the main objective in compressed sensing is to utilize the underlying sparsity of a signal to reduce the number of measurements. And this motivated David Donahoe to write, why go to so much effort to acquire all the data when most of what we get will be thrown away? So if we have 1 million pixels and the end will only have 20,000 wavelet coefficients, why take 1 million measurements? Why go to so much effort? And another thing in this design space that we need to think about, we understand that we want to minimize the number of measurements. We need to realize that the measurement process is always going to be analog, or almost always. And we discussed different types of sensors, different acquisition systems, and analog systems are going to contain noise. They're going to contain nonlinearity, so it's not going to be exactly A times X. There's going to be crosstalk between wires. There's distortions, a lot of problems. And for ease of analysis, we're going to be assuming Gaussian noise. And this can be generalized to non-Gaussian noise, for example, by Guo and Rong, and also by Rangan and later with his co-authors. So here's our signal and measurement model. So again, I want to minimize the number of measurements. I am allowing for noise. We're saying that noise is very important. And my signal and measurement model, let's look at the signal x, the vector x. X is again going to be of length n, and location number n, xn, will be a product of two terms, bn and un. Bn is going to be a Bernoulli variable. Bernoulli with probability epsilon. And un will be distributed according to a distribution, a PDF, a probability density function, pu or fu, whatever notation you prefer. And un will be multiplied by bn, giving us this orange box. Now you'll note that in the past I did blue boxes and white boxes, and here I'm doing colored boxes because the actual non-zeros are going to get different values as determined by un, and un again is driven by this distribution. And the bn's are i.i.d. Again, they're Bernoulli, and assuming that epsilon is small, that would mean that overall x would be sparse, but x could also be not so small. So indeed, let's also realize that we could be looking at a non-sparse input x where epsilon is equal to 1 and xn is equal to un because bn is always equal to 1. So our model allows for sparsity, but it also allows for this i.i.d. input. It's a somewhat flexible model. Now we have x, we're multiplying it by a matrix phi, and y0 are the noiseless measurements, phi times x, but we're multiplying them by square root of gamma. Gamma will be soon explained to have a operational importance in terms of the signal to noise ratio, SNR, and we're adding measurement noise z. So square root of gamma phi x plus z is equal to the noisy measurements y. So let's go through this step by step. First of all, the matrix phi is going to be assumed to have unit norm columns. Because the matrix phi has unit norm columns, each of these entries in X, let's say xn, is being picked up by phi n, the corresponding column. So phi n is being multiplied by, or xn is being multiplied by phi n. And if phi n has unit norm columns, and by the way, it doesn't need to be necessarily always unit norm for every single column. It could be unit norm on average in an i.i.d. matrix. That's one possibility. And under this assumption, basically we can multiply this construction by phi transpose. And if we multiply everything by phi transpose, let's think what we're going to have here. Phi transpose times y is equal to square root of gamma, which is a scalar, so we can put the phi transpose inside the parentheses, times phi transpose times phi times x plus phi transpose times z. Now, if you think about it, phi transpose times z is a Gaussian random vector. And I mean, z is i.i.d. Gaussian noise, okay? So it's a Gaussian random vector multiplied by phi transpose, meaning that we still have a Gaussian random vector. Gaussian random vector multiplied by matrix is always a Gaussian random vector. So we can characterize for this Gaussian random vector, all we need to characterize it is the expected value and the covariance. That's it. That'll give us the entirety of this multidimensional probability density function for this vector. Now, what about square root of gamma times phi transpose times phi times x? So recall, phi transpose times phi is near diagonal. We had that discussion when we were looking at cosam. And indeed, because we have unit norm columns, phi transpose times phi is near the identity matrix, because along the diagonal we'll have ones, because these are unit norm columns. So therefore, square root of gamma times phi transpose phi x is approximately square root of gamma times, well, phi transpose phi is approximately the identity, so I'm just multiplying by x. That's it. So we're left with square root of gamma plus, it turns out that the other term, the phi transpose times z, because the phi has, again, unit norm columns, it turns out that we'll have a Gaussian random vector, and the variances are 1. Each of the elements in this Gaussian random noise vector is going to be 1. And that's why, because we have square root of gamma times x plus that Gaussian random noise with variance 1, that's why gamma is the signal to noise ratio. We're multiplying the signal by square root of x, which means that the energy in the signal will be multiplied by, instead of square root of gamma, we'll be multiplying the energy by gamma, whereas the energy in the noise will be 1, and the signal to noise ratio is gamma. So that's our measurement noise model. And here's an earlier result for this type of model. This is a result from 2006. We model the process from the noisy measurements to the noise, from the noiseless measurements y0 to the noisy measurements y as a measurement channel. And now, if you think about it, let's think about an analogy to a communication system. X is your input to a communication system. And in a communication system, we have a source encoder, data compression. followed by a channel encoder, meaning that we're encoding the bits at the output of the data compression for the channel. We're creating a waveform, and data compression plus channel encoding is replaced by compress sensing measurements, which really means that we're multiplying by phi. A linear encoder. Linear meaning we're multiplying by a matrix, that's it. Then we have the channel. Y0, the noiseless measurements are noises being added up to give us the noisy measurements Y. And at the output side of the communication system, the decoder, first we have a channel decoder that tries to give us, let's call it U. So this would be U hat. And then U hat would be presumably very close to the output of the data compression, which means that when we apply the decoder to the data compression, the source decoder, we get X hat, which hopefully is very similar to X. But again, in the communication system, we have two blocks. And here we have compress sensing decoding or sparse recovery. So there's an analogy to communication systems. And part of the analogy is that just like in a communication system, measurements through the channel provide information. Here in the compress sensing system, measurements that go through this channel provide information. And this analogy to an information theoretic system, a communication system, led to a preliminary single letter bound for compress sensing and indeed linear measurement systems. By linear measurement, I mean anything where we have matrix times vector plus noise. So it was a preliminary bound, a bound, not a precise result. So we knew that the quality of the compress sensing reconstruction cannot be better than some expression. And after our result in 2006, at the same time, there were various other results that were similar. There were other single letter bounds by a lot of authors, including Aaron Zhao and Sally Grama in Boston, Aksakai and Tarak at Harvard, Rangan, Fletcher, and Goyal. Rangan is currently at NYU. Fletcher at that time was at Berkeley. Goyal, at the time, I believe, was at MIT. Gaspar and Reeves, they were at Berkeley. A lot of authors, okay? There was also a literature in belief propagation and multi-user detection. And in particular, Tanaka, Guo, and Montanari were characters that led to the development later on of approximate message passing, which we're going to discuss in an upcoming module. There were also belief propagation algorithms for compress sensing. Different authors such as Rangan, who I mentioned earlier, discussed arbitrary noise. There were a lot of different results, but in 2009, there had been bounds, but not a precise understanding. And what I'll do in the next module, I'll show you an information theoretic result that gives you a precise understanding, not a bound, of the reconstruction error in the limit of large systems, meaning that the matrix is large, the signal becomes long, the aspect ratio of the matrix is fixed, and for an i.i.d. matrix, we'll see exactly what the quality of the reconstruction can be. So that'll be all for now.